The Arduino Pro Micro is perfect for creating custom USB keyboard and mouse projects. So let's use one to turn this ZX Spectrum into a USB keyboard for the Fuse emulator. Hi and welcome to Bytes and Bits. A while ago I bought myself a Spectrum case and keyboard, and that was to build a replica machine using a bare metal emulator running on a Raspberry Pi. Now if you do want to have a look at that project, then please head over to this video. But I have to admit I wasn't completely satisfied with the outcome of that project. The emulator was great for playing games and messing around with the computer, but it didn't have any way to save either the state of the machine or to save data onto a tape. So as I wanted to have a play around with basic coding on the Spectrum, this would mean having to type in all my code from scratch every time, and this really just wasn't usable. So in this video, I'll be taking a different approach. I'll be using the Fuse Spectrum emulator running on a Windows PC, and then I'm going to rebuild this case into a USB keyboard. And that's so then I can use it as a normal Spectrum whilst running the emulator. So all of the Spectrum's multifunction keys, that they will work as normal by mapping them to the relevant PC keys, along with the cap shift and the symbol shift keys to get the full range of keywords out of this keyboard. So let's get started by looking at the hardware and software that we're going to need to be able to make this project. So the ZX Spectrum keyboard is actually a membrane construction with the key contacts arranged in 8 rows of 5 keys. Now this gives us the standard rubber key layout from the original machine. Now if you do have a later model like my Spectrum Plus here, then you'll have some extra keys on the keyboard, but these are, well, they're sort of fake keys. They actually reproduce some useful functions from the standard layout, but they do this by pressing 2 keys at once on the keyboard. For example, pressing this delete button is actually wired in the membrane to press both the 9 key and the cap shift key together. So from a hardware perspective then, any Spectrum keyboard can actually be handled with the same 8x5 matrix. Now if you look at a Spectrum keyboard membrane, you'll see 2 ribbon cables with the row and column connections. Now these are the raw matrix wires from the switches, so we need to wire these into our control circuit correctly to make them function. Now the basic idea for any keyboard is to use this sort of matrix circuit so that we can monitor many more keys than we have I/O pins. So the row and column wires are arranged in horizontal and vertical tracks, with switches connected across the intersections. So the column wires are held high through pull-up resistors at one end, but then connected to input pins on our controller. So the row wires are connected to output pins from our controllers, which are initially held high as well. So in this state, pressing any key will have no effect on the state of any of our column input lines. We can now activate a row of keys by pulling a single row wire low. Now, when any key in that row is pressed, it will connect its column line to 0 volts, pulling it down and providing a low input signal to our controller so that we can detect that that key has been pressed. And after that then, we just simply turn that row off and repeat the process for all the rows in turn. Now with this basic matrix, we do have to consider what happens when more than one key switch is being pressed at the same time. So if we are scanning a row and a key is depressed, it connects its column to 0 volts. If another key in that column is also pressed, it will try to connect its same column line to its row line, which of course is at 5 volts. And this could potentially cause a short circuit, or at least it's going to leave our column line in some sort of undetermined state, giving a bad key press reading. So to get around this, we simply add a diode to each of the row lines, and that then blocks the 5 volt signal from filtering back up to one of the inactive rows into a column line. So we're going to need a microcontroller to handle all of this, and as we can see, it's going to need at least 13 digital I/O pins. We're also going to need an easy way to connect it to our computer as a fully functioning USB device. Now this is different to just creating a simple serial port, as the controller will need to identify itself as a keyboard and handle the full USB interface. Now our microcontroller doesn't need to be very powerful. It's not actually doing very much, just sort of scanning a few inputs and outputs, and therefore it doesn't need to have much RAM or flash storage. So for this, I'm going to use an Arduino Pro Micro. Now this is a variation on the Arduino Leonardo, and it uses this ATmega 32U4 microcontroller. Now the big advantage to this chip is that it has full USB support built in, whereas if we were to use the standard Arduino Uno, which uses this ATmega 328P, then that does need some extra help to actually turn it into a USB device. So this controller just makes the whole process that much easier. It also means then that the Arduino library contains a very useful keyboard and mouse driver library that we can very easily use to turn this particular type of microcontroller into either a full keyboard and or add mouse functionality as well, and that's almost with no configuration. So let's grab hold of one of these boards and test out this keyboard library just to see how that all works. So in your Arduino IDE, make sure that you first of all update all of your libraries and your board definitions. Once those are all up to date, if you then go to your File menu, into the Example section, you'll see a USB section, and inside there a Keyboard section. And inside there we have some example bits of sketches, and we're going to try out the keyboard serial one here to get some code up. And once you load it, this is the code that you will then see. Now, as you can see, there's not actually a lot in this, and we don't really need very much to get the Arduino to actually start sending keystrokes back to our PC. So if you look through this, we simply then need to include this keyboard library up at the top of our code. And it then needs to be initialized in our setup function, so just this keyboard.begin method call. And then once we get into our main loop, we can simply then write key data out to this keyboard object. And that will then handle sending that back to our PC as an actual keyboard key press. So if you now plug in your Pro Micro board and set up the IDE to use that as a Leonardo board, then you should be able to compile and upload your sketch onto the Pro Micro. Now for this example, if we simply open up the serial monitor, what it's going to do here, as we type a letter into the terminal, once it's sent down to the Arduino will monitor that and then just simply send back a key press for the letter in the alphabet, one above the one we sent down to it. So we should then get, if I send down an A here, we should get a B coming back. So if all this is working correctly, then we're all set up and ready to go. So obviously we're going to need to connect this all up to our ZX Spectrum keyboard. So the full circuit that I'll be using is shown on the screen now. So our power and USB connections will simply be provided through the main USB-C connector on the Arduino Pro Micro. We're going to use this to both program the board, and then once we've programmed it, it's actually going to provide the USB keyboard connection back up to our PC. Now after that, we just simply need to connect the row and column signals to our I/O pins, and we're pretty much all set. Of course, making sure that we do include these feedback diodes in here, or these blocking diodes. Now for my circuit, I'm also using an extra push button to give me an extra level of control on the board. Now on my Spectrum Plus case, I've got a handy reset push button on the left hand side. But if your case doesn't have one of these, just wire any sort of switch that you have up to one of these inputs. Now this is the built-up circuit actually mounted in the case. So I'm building it up here on some of this matrix board. I'm using 2 ribbon cable connectors to capture the cables coming off the ZX Spectrum membrane. And you can actually easily find these on eBay. So I'm going to mount these in the same place that they would be on the original motherboard, so as I don't bend or stress these ribbon cables, that they are a bit fragile, so you really don't want to be bending them too much. I'm then mounting the Arduino on the bottom of my matrix board, so that when I mount it on standoffs, my USB connector is going to be easily accessible through the edge connector port at the back of the case. So that's pretty much all there is to as regards circuitry for this project. We now need to make sure that we actually get some software to drive this. Now, as these Pro Micro boards are they're pretty ideal for keyboard and mouse circuits, there are some really great third-party libraries that you can use to create some very complex arrangements. Now, I'm going to leave you to have a look at those yourselves, because in this video, we're actually going to write our own driver, just so that we can see how everything works and just customize it exactly to what we want to do. So the code I've written is in this sketch that's on the screen at the moment. Now, I'll be sticking this into a GitHub repository so you can download it, and you'll find links below and on my main project page at my bytesandbits.co.uk website. Now, I have written it so that you can easily modify it to any keyboard that you want. Again, as long as you've got enough pins on your Arduino to connect it all up. So the way I've coded this program is to break up the task into functional blocks. So we'll first of all go through the normal setup function to get the system up and running, and then we're going to use the main Arduino loop to run this repeating scan timing. Now for this, I'm going to run my scan around about every millisecond or so. So looking from the start of the code, we start off then by first of all including our keyboard library. We're then going to define our matrix size for our keys, and then I'm using this one here for a debounce timing setting, and we'll come across what that does in a little while. So we're then going to define our I/O pins, and then I'm going to place them into two arrays for our rows and our column pins. So having them in arrays will make it a lot easier for us to step through the pins using a simple for next loop. So I'm also defining the input pin here for the extra push button, and then we're going to go off and create our key code lookup table. So this is a two-dimensional array, and that then mimics, of course, our 8 rows of 5 columns on the keyboard matrix itself. Now you'll see here that I'm using my predefined constants instead of actually typing in the numbers 8 and 5. And again, that's to make sure that we can avoid having these ideas of magic numbers embedded in our code. So anywhere in the code where we need to reference the size of our keyboard matrix, it will use these predefined values. So if you ever need to use this code for another different sized keyboard matrix, again, you can just simply change the defined values, and then all the software will then sort of fall into place. So again, just always trying to avoid embedding magic numbers into your code. So the key code positions then, all of the codes here are taken from the Spectrum keyboard documentation. And again, this diagram on the screen here, and I'll put a link out to where I got this from as well. That just shows you how that matrix is actually laid out. Now, most of the keys are self-explanatory, but of course we do have the special cap shift and symbol shift on our Spectrum keyboard, and those need to be mapped to the keys used by the Fuse emulator so that it can mimic those functions. Now you'll notice that our key map simply covers the base key codes relating to each key. The shifted states and the other values will all be handled by the PC, with us just telling it when certain keys are pressed and then released. So for example, the equal symbol is a symbol shifted L on the Spectrum keyboard. So our code is simply going to tell the PC that someone is holding down the left control key. And again, you can see we have that constant from our keyboard library defined there. And then, of course, that's being held down together with the L key. Now these special key codes, as I said, all of these constant definitions then are in the Arduino Keyboard library. And if you want to get a full list of all the keys that you can actually simulate, which is pretty much every key that there is actually, then do just check out the documentation of the library for that. And again, I'll put a link in the code so you can go off and find that quite easily. So we're now getting into the main meat of our code. And here I've modeled the task that we're doing with two C++ classes. And these model the individual keys that are then placed into a matrix. So this first class, called Keyboard Key, that understands how to read a single key and then correctly send its state back to the PC. So when we instantiate or create an instance of the class, we're going to tell it its location in the matrix, and you can see that in this constructor function here. So it will then go off and collect a key code for that position in the matrix from our key map, and then stores that inside one of its variables for future use. So it then waits to be told when to scan its key, which would then be called using this update key method. So update key, first of all, it assumes that the relevant row line has already been activated by the matrix driver class, which we'll see in a second. So all it does here is it checks the current state on the key and compares that then to the currently reported state. So I'm saying here currently reported state, as we need to be careful about when we actually detect a switch state change. So mechanical keys, and especially lower quality ones, which of course very much relates to the ZX Spectrum, that they don't give a clean connection when you press them. They actually do what's known as bounce. So a single key press can actually result in multiple ons and offs for a very short period of time as the two pads of metal come together to make the switch contact. So to combat this bouncing, we need to look at the state of the key on each scan and then wait for it to stabilize. So once we see the state has changed and stayed constant and stabilized for a number of scan cycles, then we can log the change and send a key action. So that's what this debounce counter does. It simply lets us count how many scans we have completed looking at the state change on the switch. And if we then reach 5 in this case, so 5 milliseconds worth of debounce, then we can say that our key is stabilized and we're now getting the true value of the key press action. So that gives us our key press action. The actual key data then that we're sending, we're using a much more basic method than the full character codes that we saw in the Arduino keyboard serial example. So we'll be sending a signal to say when a key is first pressed down, and then a second signal when it is released. So in this way, the PC actually knows which keys are currently being held down at any one point in time. And that's how it works out whether we have the shift and control keys modifying any other key's behavior. So that's that class all done out. So after the class definition then, we need to create our key handlers array. So we're going to set aside some space here for 40 keyboard key objects, so one for each button on our ZX Spectrum keyboard. So with that all in place, we now go into our matrix driver class, and this is the class that will actually run the scanning process. And it really only has one main method, this scan matrix method. So what we do in here is we are simply going to step through each row, and we're going to activate that row signal line and then take all the others into their inactive state. And we do that using this activate row line method. So once that line is active, we then ask each keyboard key object on that row to scan its key before then moving on to the next row. So our activate row line method then, it just simply makes it very easy to turn on a single row. All we need to do is to tell it which row we want to be active, and it will then turn that one on and then deactivate all the rest for us. So after this class definition, again, we just need to create another global variable which is going to hold an instance then of our matrix driver object. So next we come to our setup code, and this is fairly standard, apart from an initial pause state. So when we use the keyboard library, it can take over the USB port. So if something goes wrong in the code, it can actually leave you locked out of your Arduino. And that makes it hard to get back in because, of course, every time you power it back on, it runs your sketch, bombs out again, and leaves that USB port disabled. Now this little loop here at the start of my code, it simply looks at the state of that extra push button that we added, and it doesn't let the rest of the code run until we press it and say so. So if our code is broken, we will crash. We'll just simply reset the system. And when we come back in again, we'll have this pause in place. So at that point, of course, we can get control of our USB port and then reflash our code. So after that then, we're just setting up all of the I/O pins as usual, making sure that our column pins are set as inputs, but using the internal pull resistors so that we don't have to add any external ones. And then we jump into a for next loop. We're simply creating instances of our keyboard key class and then assigning them to their position in the keyboard matrix and storing them in this key handlers array. So by the end of this little loop, we're going to have an 8x5 array of keyboard key objects, each of which then knows which key it's responsible for and is now able to actively scan and process those key presses. So after that then, we're into our main loop, and the way we've structured our code, it makes our main loop become really simple. So all we're doing is we're going to pass all of the control over to our matrix handler object, and we're just going to simply ask it then to scan the matrix. After it's finished, we're going to wait for 1 millisecond, and then we're going to go back around and repeat it. And that gives us our, okay, it's a little bit more than 1 millisecond because of course we have to take into account how long it takes to scan the matrix, but in effect we are pretty much scanning once every millisecond. So that's everything all coded. So all we need to do now is to get our keyboard plugged in and flash that code down to our Arduino and do some testing. So I've opened up Notepad on my PC, and again I've got my Spectrum keyboard plugged in over USB. So to begin with then, of course, we're in this holding loop, which is going to give us our sort of escape if we do something wrong. So if I press any buttons at the moment, nothing happens. But then of course, if I press that reset button, which is just behind my keyboard on the left-hand side here, now we should find that my keyboard is working. And as you can see, the keys are operating as normal. So with the ZX Spectrum keyboard, we've basically got a full set of number and letter keys along with our shift and control. That the return button works as a normal return. But of course, when we use shift with some of the keys, we're getting capitals rather than any of the Spectrum stuff. So we're going to need to power up our Fuse emulator to be able to see it working as a Spectrum keyboard. Now, if you've got to the stage and you're getting some strange characters coming up, or characters that don't match with the buttons that you're pressing, then of course all that's happened there is you've probably got your matrix wiring a little bit messed up. So do go through and check that. So then as our final test, of course, we will power up our Fuse emulator here. And again, that takes us into our normal ZX Spectrum startup screen. And here we should now have our ZX Spectrum working as, well, as a ZX Spectrum. So as I start typing in here, you can see that we can type in our code and we're getting access to all of the special Spectrum functions and keywords and so on. Again, using my symbol shift and cap shift and extended buttons, I can gain access then to all of the other functions as well, and also the graphics and so on. So it's working as a proper ZX Spectrum keyboard. Now, one of the good things as well with this method, so remember we were using the switch press and the switch release functionalities in the keyboard system, and then just letting the PC actually handle what that actually means. So if I do hold the key down here, because those keys are being held down, the repeated key presses, of course, are being handled by the PC's keyboard driver. So we don't have to worry about doing those repeated keys when something's held down. We're just simply telling the PC that this key is being held down and it will do all the rest for us. So that gives us then a fully working ZX Spectrum keyboard running over USB using the original hardware, and then everything being done by our own keyboard driver running on our little Arduino Pro Micro. So hopefully that's given you enough information to understand how this keyboard driver works and how you can then use that to create your own little keyboards, either out of an old computer or whatever. A lot of people actually use this technique to build little macro keyboards to give them sort of shortcuts on various applications. And again, there's lots of videos on those out there as well. A lot of them use the more complicated library-based keyboard drivers, which give a lot more features, but hopefully you've seen there that the general process is not so hard, and we can simulate a range of keys just with our little basic driver here. So I hope you find that useful. If you've enjoyed that, please do click that like button and consider subscribing to the channel for more making, electronics, gaming and modding videos. I look forward to seeing you again very soon, and bye for now. For more games programming, electronics projects and retro gaming, please make sure you like this video, subscribe to my YouTube channel and visit my website.